We're next going to look at the concept of inductance. We've talked about induction, right? Induction is a process by which an EMF is generated by changing magnetic flux. So that if the magnetic field strength changes, the area changes, or the angle between those two things change with time, you can induce a current in a conductor. An EMF is established that pushes the current. Now the inductance is a measure of how effective a device is at inducing current. There are actually electrical circuit components called inductors, which we'll talk about in a moment, that are designed specifically to develop a magnetic field when the current starts up and will create, of course, current in the presence of a changing magnetic field. So, mutual induction is when one device, the changing current in one device, creates a magnetic field in the second device, and vice versa. So here we have a simple AC circuit, alternating current circuit of some potential. So the current is flowing back and forth, back and forth, back and forth through this coil of wire. Now, as current flows through a wire, we know that magnetic field is generated. And in a coil of wire, the magnetic field at the center of the wire is given, well, we calculated what that was. Or we will shortly, my apologies. The magnetic field in this coil creates these magnetic field lines. I don't have the direction drawn here, but we'll assume it's going to the left. If those magnetic field lines pass through a second coil, as these magnetic field lines get stronger and weaker as the current changes direction. So this is a magnetic field currently, but then the current will change, go to zero, meaning there'll be no magnetic field, and then the current will go in the opposite direction, so this magnetic field will flip in the opposite direction, and then back and forth, back and forth, back and forth. So the magnetic field in this second coil is constantly changing strength. So while the area in this second coil isn't changing, and the angle between the loops and the magnetic field isn't changing, the strength of the magnetic field is changing with time. So the magnetic flux through this second loop is changing with time. Since the magnetic flux is changing with time, a current is induced in this second circuit, and we can measure that current through this galvanometer. Note that these two devices are not physically in contact with one another, but the changing current in one can generate current in the other. How much current? Well, it depends on the EMF. The EMF of this second coil is equal to minus, because again, Lenz's law, the EMF is always a back EMF. It opposes the changing current, the changing flux that's currently through the coil. So if the current is increasing, then the EMF is established to try to prevent that from happening. If the current is decreasing, an EMF is established to try to prevent that from happening. So it's minus what's called a mutual induction value, M, times the change in current from loop 1 with time. How quickly is the current changing with time? Alternatively, the changing current in coil 2 generates a magnetic field in coil 2, which goes through coil 1, which generates a current in coil 1. And an EMF in coil 1, the amount of the EMF is equal to minus the mutual inductance term divided by how quickly the current in the second coil changes with time. So note that they're similar setups, but they have this M term, which we haven't seen before. That M is the mutual inductance term. It depends upon the physical setup of the coils, how closely spaced are these coils, and things like that. M is the mutual induction between two devices. How efficient is one device at generating current for another device? It is measured in units of henries. So mutual inductance term is in units of henries. And again, it's not some universal constant. It depends on the setup that we have. Mutual inductance is when two devices induce a current on one another. So the original device has some oscillating AC current, which generates a changing magnetic field, which creates a changing magnetic flux. That changing magnetic flux goes through the second coil, generating a current in the second coil. That current in the second coil generates a magnetic flux that affects the first coil. Self-inductance is when you have a single device, coil of wire, And when the current in the coil of wire changes, the magnetic flux increases. And what happens is when the magnetic flux changes, a back EMF develops. An EMF is created to oppose the changing magnetic flux. So, in an inductor, a device that undergoes self-inductance, the EMF is equal to minus the inductance of the inductor, we'll talk about what that is in a moment, times the changing current with time. So the current changes with time, then you have an EMF can develop in this coil of wire. How big that EMF is depends upon how quickly you change the current and the inductance of the inductor. Just like the charge on a capacitor depends on the voltage and the capacitance of the capacitor. The inductance of the inductor, which has units of henries, is dependent upon the size and shape of the inductor. Now, there are many different configurations you can put for coils of wire. The simplest coil of wire is just so the inductor symbol is either these humps, so it's not a sawtooth pattern like a resistor, or it's also can be written as coils, actually showing the coils. The simple coil, a straight coil of wire of similar diameter throughout, same spacing of coils throughout. This is called a solenoid. It's the simplest version of an inductor. Now the inductance of a solenoid is equal to mu naught, the constant we've been dealing with in the last chapter, the total number of turns squared. So how many turns of wire are there in this solenoid? Multiply that number by itself, so square that number, times the cross-sectional area of the solenoid. So if the solenoid is a big cylinder, what is the cross-sectional area of that cylinder, or how big is the circle at the top of the solenoid, divided by the length of the solenoid. So a lot of windings means it's a strong inductor. A big cross-sectional area means it's a strong inductor. A large length means that it's a weaker inductor. So you need a lot of tightly packed coils in a small space to increase the inductance. Now the inductance of the inductor, again, depends on the physical makeup. You can see here is the number of spins of coil, the cross-sectional area, and the length. Nowhere in here does it depend upon the current. Right? The inductor is a physical makeup. The inductance of the inductor doesn't change if you have current going through it or not. Just like the capacitance of a capacitor doesn't depend upon the voltage across the capacitor. It depends on the physical makeup of the capacitor. For a solenoid, the inductance depends on the physical makeup of the solenoid.